Growing up, I would eat ice cream all the time in the summer. And I'd bring those little Baby Bell cheeses, the ones that are covered in red wax.
Yeah, I know what you're talking about. I love those.
Yeah, I'd bring those to school in my lunchbox most days of the week. What I'm saying is that I ate plenty of dairy as a kid, and I felt totally fine. But then, as I reached my late teens, that began to change fast. It started with ice cream and milk. When I had milk and cereal, about an hour after eating it, I'd get these terrible stomach cramps and be running to the bathroom. I'll spare you the details. And about a year after that, I started having the same thing happen with yogurt and anything that was creamy, like Alfredo sauce on pasta. That became a hard no. Then a couple years after that, cheese had to go too. I think of all of the things, I miss greasy, late-night pizza the most. So, in just a few years, I went from essentially no issues with dairy to major GI issues when I ate any dairy. So, what happened? Welcome to Tiny Matters. I'm Sam Jones, I'm lactose intolerant, and I miss greasy pizza.
And I'm Deboki Chakravarti, and I am not lactose intolerant. And I thoroughly enjoy greasy pizza.
Very lucky. Today on the show, we'll be talking about why I used to be able to eat dairy, but now I can't, and why that's the case for so many people all over the world. We'll talk about the difference between a dairy allergy and lactose intolerance. And we'll hear from a geneticist who's spent years studying the evolution of humans' ability to break down lactose. Very recently, he and his colleagues made an interesting discovery.
Let's start with the basics. What's a dairy allergy versus lactose intolerance? If you're allergic to dairy, your body negatively reacts to proteins like casein that are found in milk and other dairy products. Your immune system sees those proteins as foreign invaders, kind of like it sees some other allergens like pollen or a pathogen like bacteria. A dairy allergy can cause anything from a mild rash to difficulty breathing. If you're lactose intolerant, your body doesn't make enough of an enzyme called lactase. Lactase breaks down lactose, which is a sugar found in milk. Without lactase, you're not able to digest lactose, and that can cause some serious gastrointestinal distress.
Yep, can confirm. And even things like Lactaid, which are pills with that lactase enzyme, still don't work for me, and they don't actually seem to work for a substantial number of people. There was a study that came out in 2014 that showed that about 20% of people were like me. Supplemental lactase didn't help them. If you're one of those people, you might not be taking enough of that lactase or enough for the amount of dairy that you're trying to eat. Or your timing is off and you're not taking it early enough before you eat, or you're taking it too early. I don't know. I mean, I really feel like I've tried every iteration under the sun, and it's always a no-go. No matter how much Lactaid I take, my GI tract is still very, very unhappy anytime I encounter lactose.
We'll talk about that GI stuff in just a second. But first, let's further complicate things. If you don't produce that lactase enzyme, you're considered lactase non-persistent. However, just because you're lactase non-persistent, that doesn't necessarily mean you're lactose intolerant.
Lactose intolerance is very difficult to define and pin down, but lactase non-persistence, which is the main thing that causes lactose intolerance, is very easy to define and reasonably easy to predict from genetics.
That's Mark Thomas, a professor of evolutionary genetics at University College London in England.
So, if you don't have the enzyme lactase, then in theory, you should be lactose intolerant. But in reality, 2/3 of the adults in the world today don't produce lactase, and yet only a very small proportion, mostly people in the West, complain about lactose intolerance. So that relationship, which in the past has been treated as almost a one-for-one, is clearly not the case. Many people don't produce lactase, but don't really suffer any major symptoms from consuming lactose-containing foods.
So let's say you are lactase non-persistent. You're not producing that lactase enzyme. And you seem to be lactose intolerant, like me. What's happening in your body? Well, instead of digesting lactose like you normally would in your small intestine, the lactose would cruise on down to your large intestine undigested. One of the jobs of our large intestine is to reclaim the extra water that comes from waste, recycling it back into your body and your bloodstream. Lactose totally messes with that process, throwing off the osmotic balance and essentially liquefying the stuff in your large intestine.
That leads to one of the first consequences of consuming milk or lactose if you're not producing lactase, which is that you get diarrhea. But also, that lactose in the colon is digested by a range of bacteria. They produce a range of byproducts like fatty acids and various gases, especially hydrogen. And hydrogen, well, it's gas. And as you might guess, there's pretty much one main route out. But actually, hydrogen is actually quite a soluble gas. So some of it actually gets absorbed into the blood and then it comes out in the breath, in the lungs. One of the methods we use to test whether somebody's producing the enzyme lactase is that we'll give them about 50 grams of lactose, which is the equivalent to about a litre of milk. And then we measure the hydrogen coming out in their breath. And normally it hovers around 10 or 20 parts per million. It's a very small amount. And then after about an hour and a half, if it shoots up to about 300 or so parts per million, then that means that the lactose has got to their large intestine and been fermented and made hydrogen. So they're not producing lactase. So it's one of the tests we use. It's not foolproof, it's not 100% reliable, but it gives a reasonable indication of whether somebody's producing lactase.
I didn't realize that you could look for a digestive issue with a breathing test, and that is really wild.
I know, I had no idea either. And now I'm very curious as to what my numbers would be if I did that test. But maybe I'm not curious enough. So, in addition to the hydrogen breath test, there's a test where a person drinks a beverage with a lot of lactose. And then, about 2 hours later, the amount of sugar, specifically glucose, in their blood will be measured. Why glucose? Well, like Deboki mentioned earlier, lactose is a sugar. It's actually a disaccharide, meaning it's a sugar made up of 2 sugar molecules. One of those sugars is galactose, and the other is glucose. So if you're producing that lactase enzyme and breaking down lactose, you should have a bunch of glucose in your bloodstream. If you don't, there's a good chance you're lactase non-persistent and possibly lactose intolerant. So now, Deboki, let's dig into why I was able to digest lactose as a kid, but cannot digest it anymore. Why can't I eat birthday cake remix ice cream from Cold Stone anymore? This is not an endorsement. I just really miss it.
Well, Sam, you may have been able to eat that birthday cake remix ice cream when you were a kid because, as it turns out, basically all of us start off being able to digest lactose.
So all infants produce lactase, or virtually all infants produce lactase. But then about 2/3 of adults in the world, some point after the weaning period is over, the production of lactase drops to very low levels, such low levels that it's effectively absent. I'm lactase persistent, so I continue to produce lactase. But 2/3 of adults in the world are lactase non-persistent, so they stop producing lactase. It's genetically determined. It's what we call in genetics dominant. So that means that you only need a gene from your mother or from your father that allows you to produce lactase and you'll carry on producing it. But we don't know the ultimate evolutionary reason why that happens. But interestingly, as far as we're aware, it happens in all other mammals as well. And if you go back 10,000 years, virtually every human as well would downregulate their lactase after the weaning period is over. And what that means is that if they consume milk or they consume something containing lactose, they won't be able to digest it.
So the genetic record tells us that 10,000 years ago, almost every adult was lactase non-persistent. They weren't producing that lactase enzyme. In other words, they were like you, Sam.
I guess I have more in common with our ancient ancestors than I thought.
Those genetic changes, we can look at them in DNA that we get from old bones, so from ancient DNA. So we can get an idea of its distribution in the past as well as today. And it's very clear that it's increased in frequency dramatically over the last 3,000 or 4,000 years.
It's only over the last few thousand years that a substantial number of people are able to digest lactose. This is a trait that researchers like Mark think evolved independently all over the world. Today, it's often talked about as being a European thing, but lactase persistence is found everywhere.
Outside Europe, it's found at appreciable frequencies in Southern Asia, so in India, Pakistan, in the Middle East, and in many African populations.
With evolution, genetic mutations pop up randomly, and if they're advantageous for some reason, then they might get selected for and become more common in a population over hundreds of thousands or millions of years. But lactase persistence became common in just a few thousand years. That's unheard of on an evolutionary timescale.
Basically, what that tells us is that in terms of genetic traits, the one that made the biggest difference to life or death over the last 5 or so, maybe even 10,000 years, is one that simply determines whether we can digest the sugar in milk or not. Now, you can get by without digesting the sugar in milk, so it's quite a weird thing, really. It takes some explanation, and in fact, people have been speculating for a long time about what the big advantage to being lactase persistent is.
One idea scientists have had is that milk provides vitamin D, something Mark says is pretty important for Northern Europeans in particular because of the lack of sunlight in Northern Europe. Sunlight, specifically UV rays, convert cholesterol in your skin cells to vitamin D, which you need to absorb calcium. And calcium is important for not just bone strength, but tons of things that happen in your cells. Another possible reason that lactase persistence became so common so quickly was that milk was relatively clean and safe compared to even the water that might be around. So that could have been a big advantage for our ancestors' survival.
Mark told us that over the last decade, the ancient DNA field has come a very long way. And scientists now have more tools, better tools, to learn about the people who died thousands of years ago. So, with ancient DNA in hand, Mark worked with colleagues at the University of Bristol to analyze if increased lactase persistence had something to do with an increase in milk consumption. In other words, did it pop up more in places where people were drinking milk? They looked to ancient pottery to try and answer that question. Researchers at the University of Bristol had developed methods for extracting fats from broken pieces of pottery from thousands of years ago. By looking at the molecular structure of those fats, they could determine if the fats came from, say, a dead animal, or plants, or milk. They looked at more than 5,000 pieces of pottery from all over Europe, and then mapped changes in patterns of milk consumption across the continent.
And the results were really quite shocking in that the answer is no. No, it doesn't. So if you assume that natural selection was constant over the last 9,000 years, the evolutionary process is just as probable as it is if milk use is controlling it. So that's weird, right? Because all of the theories about the advantage are pegged to milk use. All of them predict that there would be stronger natural selection if there was more milk use. And we didn't find that at all.
So they were back to the drawing board. What else could be driving that super strong natural selection for lactase persistence?
Mark told us a couple of other theories that had been proposed. About a decade ago, he'd hypothesized that in times of famine, there would be more natural selection for lactase persistence.
Imagine that you're a healthy person, a healthy prehistoric person, but you're like you, right? You're lactose intolerant and you drink some milk. So, you're going to have to rush to the loo, right? You're to the toilet. It's not going to be nice. It might even be a bit embarrassing if other people are around, but you're not going to die, right? But if you're severely malnourished, then diarrhea can turn from an inconvenient to a fatal condition. In fact, even today, amongst severely malnourished people, diarrheal disease is a major killer. And again, it's because of gut disturbances, fluid loss, and things like that. So I predicted that in times of famine, there would be a bigger advantage to being lactase persistent.
Mark's colleague, George Davy Smith at the University of Bristol, had another idea somewhat related to Mark's. He thought that when pathogens like viruses and bacteria would become more common in a society, there'd be more natural selection for lactase persistence. Because if you're fighting off a pathogen, having diarrhea or other GI issues that come with lactose intolerance could be deadly. So they decided to use the same statistical evolutionary method they'd used before. But they needed to first figure out how to track famines and pathogen exposure over thousands of years.
For famines, we use radiocarbon dates to estimate population densities changing through time. And then we look for periods when populations goes up and then crashes down. And when populations go up and then crash down, that's probably indicating some kind of famine, right? Populations generally track food production. So that could be a marker of famines. And also, we know that pathogen exposure is going to be higher when people are living in more urbanized settlements. So when people are more clustered in their living. So we took the radiocarbon data again, and we looked spatially at how spread out or how clustered it was. And we took the periods when it's clustered as indicating more pathogen exposure.
And lo and behold, famine and pathogen exposure tracked pretty closely with growing lactase persistence.
So now at the moment, we think that's probably the best explanation is times of either or pathogen or famine exposure were when strong natural selection really happened. So it was kind of episodic rather than continuous.
But the work is far from done. Mark doesn't think that these are the only reasons lactase persistence grew.
I mean, I think we're definitely onto something here, but there are always other potential explanations as well. And people are producing ancient DNA data all the time. And there's more and more coming through. So, we used all that we could get hold of, but there's always more.
Remember, lactase persistence evolved independently in different populations of people around the world. This is just Europe. It'd be interesting to know if evolution in other places could also be because of famine or pathogens, or if there was something else going on.
At the top of the episode, we mentioned that although 2/3 of people in the world are lactase non-persistent, some of those people can drink milk and, unlike me, don't report any terrible stomach issues. Mark told us that in China, for example, most people are genetically lactase non-persistent, but China imports tons of milk, and many people don't report having issues drinking it. What gives? Mark said it could come down to gut bacteria.
Bacteria we have in our guts are determined by a number of things, including who we spend time with, our own genetics, our family background, but most importantly, the type of food we eat. And so if we eat certain types of food, we're more likely to have certain types of bacteria, which might then respond to lactose and give us worse symptoms than maybe other people with different bacteria. So I would suggest that what's probably going to turn out to be the case is that whether people who are lactase non-persistent get symptoms of lactose intolerance has got a lot to do with what bacteria they've got in their colons, in their large intestine.
I would love to know what bacteria that might be because, wow, please give them to me.
Well, it sounds like you've been very scientific about the whole thing anyway. So that's, so it sounds so you almost certainly are lactose intolerant, but it might be worth having checked to see whether you get worse symptoms depending on what other foods you've eaten, as well as then having some lactose, I mean, if you want to do experiments on yourself, that is, which is...
So, Sam, what do you think? Are there any experiments in your future?
Ugh, depends how much they're willing to pay me.
If they pay you an ice cream.
Not the payment I'm looking for. It's Tiny Show and Tell time.
That it is.
I can kick it off this time if you want.
Yeah, go for it.
Excellent. A few years back, scientists in Spain were checking out a research site in the field. and they came across a fox that was acting a little weird, and they realized that it was hunting a fish. They were at this site for a totally unrelated project. This was just kind of this weird moment where they felt like, okay, we need to film this. And the fox not only ended up catching the fish, but caught multiple fish. Why is this exciting? Well, this makes foxes, specifically red foxes, just the second type of canid known to hunt fish. So canids, that's the group that includes wolves and dogs, of course, foxes. It's truly just these red foxes and wolves. In the article that I read that's in Science News, one of the researchers said that fishing foxes, it's very cool because, we think we know so much about foxes and wolves and canids in general, and foxes especially, they live very close with humans, but we had no idea that they're going out there and fishing. So there's just always new cool stuff to kind of see in the world around us. I have shared the video with you.
It is so cute. It feels so much like when you're watching like a cat stalk something, like it's got like ears flat, body is just tense and moving, but then it's like very chill. It's just like suddenly dives and then there's a fish in its mouth. No big deal.
And it's a pretty big fish.
Yeah. Oh, this is so cool. I want to talk about an article that I read in Vox called Tearing Down the Academic Research Paywall Could Come with a Price. So this article is basically about the fact that recently the White House has announced that any research that has been funded by taxpayers and then gets published in an academic journal will need to be free, like be freely available by the end of 2025. And Sam, I know that you are probably familiar with all of this, but just for some context for anyone who's listening and hasn't really had to deal with navigating academic journals and like what happens with publishing, basically when you're a scientist, you get some funding, often from government sources like NIH or something. So that's where the taxpayer dollars are coming in. You do your research, you discover something really cool, you write it up for a journal, and then usually the journals, you actually kind of have to pay them for the right to publish and to accept and publish your work. And also once it's published, the journal will often put the paper behind a paywall. So if you're at a university or some other kind of institution that pays for access, you don't have to worry about that paywall, but of course, that still limits who can read those papers, especially like the public will often have difficulty accessing those papers. So there's just in general been this movement towards opening up access to these works because they're super important for the public to know. And then also like if the public has funded it, the argument is they should also be able to access it. I know for me, like I am just in the broadest sense, very pro open science, like philosophically, but I don't always think about what that means in terms of the specifics, in terms of like what the policy looks like, especially when it's implemented. And so that's what this article gets into a little bit. It looks at what similar policies in Europe have done and what kind of challenges come up in terms of implementing these ideas and the limits of how much it'll be able to do in terms of solving these bigger issues of inequality in academia. Just because you say things are going to be open, there's still like costs that are being exchanged. There's still fees being paid. It's just that the way that those fees are structured are different. And so we have to think about whether or not this still solves the underlying issue. And there's also still like a bunch of other cultural issues in academia that can compound these challenges, like the incentives around publishing and high impact journals. And so we have to think about like how these things balance each other out. So I think for me, at least, the fact that this policy might come with these limitations or challenges doesn't necessarily mean it's bad. It just points to the fact that like there's no single band-aid, there's like no single policy that's going to fix all of these issues. So I'm not suggesting that people read this article with the idea that it's meant to like dissuade you from open science, but I just think it's like a useful thing to keep in mind in terms of how we think about how we approach these issues overall.
Yeah, absolutely. I think that the opening of the conversation, particularly over the last few years, has been really interesting and I think really important because, coming from an academic background, I felt like when I was in graduate school, 4 or 5 years ago, this really was not something that people were talking about much, and it's really come to the forefront. And so I'm really interested in kind of seeing where it goes, what ends up happening. Thanks for tuning in to this week's episode of Tiny Matters, a production of the American Chemical Society.
This week's script was written by Sam, who is also our exec producer, and was edited by me and by Matt Radcliffe, who's the exec producer of ACS Productions. It was fact-checked by Michelle Boucher. The Tiny Matters theme and episode sound design are by Michael Simonelli and the Charts and Leisure team. Our artwork was created by Derek Bressler.
Thanks so much to Mark Thomas for joining us.
If you have thoughts, questions, ideas about future Tiny Matters episodes, send us an email at tinymatters@acs.org. You can find me on Twitter at okidoki_boki.
And you can find me on Twitter at SamJScience. See you next time.